last class was super important. And again, watching those two videos, I think if you really followed me, they have done the magic of telling you when we make a concrete beam and we add some reinforcement, not all the beams, they will follow the same behavior at their failure point. Not all of them, they follow the same behavior at failure. So last class, we've seen three different type of failures. And I would like to go back one more time and remind you with what was going on and what are the numbers within every failure. So we started with something called the tension failure. Tension failure. And from the name tension failure, it means the rebar has yielded before concrete crushed in compression. And so what happened at that time, the strain in the steel on the left side here, that is the strain in the steel at the failure, has exceeded the stress, the strain of the steel at the yield point. Also, the stress in the rebar simply equal to the yield point. And then finally, concrete, the strain in concrete equals to the maximum strain in concrete equal to 3.5 per thousand. And guys, we said that the failure, it's a ductile failure. It gives warning before the beam fails. The warning will be in the shape of deflection, cracking. So you will see wider cracks and much deflection. So this warning gives the occupant a chance to do something, whether to reduce the load or maybe look at the beam, maybe add extra support. Maybe the engineer will be involved to provide a reinforcement. No matter what is the reason, there is a warning and there is a time to fix that. And that's why it's a desirable mode of failure, and that's why we call it properly reinforced. Because when we say properly, it means that's the way we supposed to do if we were to design a beam. So that was the first failure mode, tension. So we call it tension or ductile or properly reinforced. And then on the opposite side, simply we have the compression failure. And from the name compression failure, this means at the failure point, concrete has taken the lead. So failed first in compression before rebar started to yield. And so simply when we look at the numbers, we see that epsilon, when we say epsilon, we're referring to the strain. The strain in the steel was before the yield, which means mathematically the epsilon S, the strain in the steel, is less than the epsilon yield. Remember, guys, this number on the right is a fixed number. For a rebar grade, it's a one fixed number. For example, for 400 MPa, this number is 2 per thousand. In terms of the stress in the rebar, as we know, for this kind of failure, still less because we are behind or beyond, I'm sorry, before the yield point. So that's why the stress in the steel is less than the F field. This number is equal to 400. And then the epsilon C maximum or the epsilon C is equal to the 0.0035% or 3.5%. And as I said, this kind of failure, it's a brittle failure because we know from strength of material, concrete is a brittle material. In tension, in compression, in shear, it does not yield like rebar. And so whenever the concrete fails first, it means it is a brittle failure. And because it's brittle, it doesn't give enough warning, and that's why it's undesirable. And we kind of discussed on very brief that what causes this beam to behave this way, it has so much reinforcement, which made the bottom bars are very strong and forced concrete to fail first in compression. Okay, now I said before last class that this picture here is a very, very nice picture to show you the compression failure. You can see at the bottom here, which we don't see the rebar, but obviously the rebar has not yielded and obviously rebar has not snapped. What failed is simply this guy here. So this guy is concrete failure in compression. Okay. Now, the last failure mode, which, as I said last class, it is a section where the failure in concrete and the yield, they happen exactly at the same moment. So when you look at the strain diagram, the same moment that rebar is start to yield, so epsilon S is equal to your 0.002 or epsilon yield, then the same moment exactly concrete will crash in compression. So you can see the word in red here, simultaneous. And if you look at the numbers, you will see the strain in the rebar is exactly, not more, not less, is exactly equal to the epsilon yield. And for the stress in the rebar is equal to the F field, because that's the start of the yield. And then finally, the strain in the concrete is equal to 0.0035. Now, if you guys remember, we said that this situation, number one, is brittle because it doesn't, the rebar doesn't go through the process of the yield. It's at the start of the yield, which means it doesn't give you wider cracks, doesn't give you lots of deflection, which means this failure is a brittle failure, brittle failure. It means it's undesirable and we need to avoid also the balanced failure by all means. Okay, that's one thing. The other thing is this beam is kind of rare to see, rare, because rare, why rare? Because the numbers have to work out so that the rebar will yield exactly at the same moment where concrete crashes, which is very difficult. You will see this in our design. It's very, very, very difficult to do a beam exactly at the balanced failure. However, although it is very rare, but you will see in our derivation, because simply the balanced failure is the stage between compression and tension. So this is a very significant moment or a state of our beam, and you will see we will have to start from the balanced failure in our derivation. Okay. Now, any questions so far? Make some noise, please. Make some noise. Any questions so far? Jelly.
Yeah, sir. Regarding the value of Fy, in this course, do we need to, I mean, is it always 400, or there is a table that Fy has also different value lower or higher than 400, and 400, and if 400, if Fy is equals to 400, Ey is always 0.002.
Okay, thank you so much. So put your hand down, please. Okay, so there was a question about the grade of the rebar. I know that you guys, like, like same semester, you're doing steel with Corwin. I know that. And in steel, things are a little bit different. So for steel, you will see W sections, they have F field. Blades, they have different F field. Angles, they have different F field. Okay, so you have to be careful for that. In my class here, if you go to the lecture where I talked about material properties, I said, in general, we have three grades of rebar, 300, 400, 500. However, I said this in my course. In my course, always, which is the most available one, we will use grade 400. That's the most available in the market, and that's why we will focus on the 400. So please take a note that in my class, always the F field is equal to 400. And if the F field is equal to 400 and the modulus of elasticity is equal to 200,000 megapascal, then in this case, the strain at the yield point, you can find this is equal to 0.002, as you can find in my lecture, material properties. Any other question before we proceed? Make some noise, please. I feel lonely. Okay, no noise? Okay, let me proceed. Okay, guys, there are in my class here, and something very, very important. You have to understand the difference between check and design. Check and design. And I know the course is called Reinforced Concrete Design. So what is exactly the check? Let me explain. So in a check problem, the information below are given. So the given are cross section, dimension. So the beam is given to you and everything is known. It means I know what's the width of the beam, what is the height of the beam. We also know the material properties like the F prime C and F field. And also we know the rebar layout. It means there is this many rebar and this with this diameter. So you can see the entire section is given to you. The entire section is given to you. So what's my job then? If the entire section is given to me, including everything, dimensions, material properties, and also rebar layout, you can see I put this in an arrow. You have to determine the moment of resistance or the beam capacity. Okay, so you will see this all the time in my class. MR, M sub R is called something called beam moment of resistance, or sometimes called beam capacity. Simply, what is the maximum moment that this beam can handle in plain English, okay? And then number two, you may be asked to determine whether a beam is safe or unsafe under a given moment, like factored moment. So another question could be, if the bending moment acting on this beam this much, what do you think? This beam, the way it is right now, is it safe or unsafe? Okay, so that's called a check problem. So we have a beam and our job is to check this beam whether it's safe or unsafe. In a design problem, things are a little bit different. So really what we have or what we need to determine is determine the beam width and height, which we call it concrete dimensions. We determine also what should be the F prime C and F sub Y, which is the yield strength, and then A sub S, which is the rebar layout in terms of number and the diameter, and then to what? To what? So we're trying to do all these things. We're trying to find all these things to ensure that my beam with these specifications will exceed its capacity, will exceed the factor the moment. Okay, so one more time in our course, you will see sometimes we do a check. So the beam is totally, entirely given to me with all the information as you can see above. And my job is to say whether my beam is safe or unsafe. In a design problem, it's reverse, which means I'm given the moment that this beam is supposed to resist, and I have to come up with the dimensions and material properties and the rebar layout to ensure that the beam will have enough capacity to handle the applied bending moment. Hopefully this is clear. And listen, guys, so like if you work as a designer after graduation, okay, what exactly are you going to do? Are you going to do design more or check more? I would say equally. Sometimes as a designer or engineers, we are asked to simply design for fresh building. So we don't have the building yet and we have all the loads and we can simply design the beam, or sometimes there is an existing building existing already and we have some drawing that contains all dimensions, all the rebar layout and all the material properties, and let's say the owner is going to change or maybe add a boiler or add or whatever the situation, and you are called to say whether this beam is safe or unsafe. And also sometimes we go further. If your beam is unsafe, you need to probably provide a solution on how to increase the beam capacity so it can handle the new applied bending moment. Are you guys following? Let me hear some noise.
Sir,
Okay, go ahead.
in in the case of safe and unsafe, is it considered safe if MR is greater than MF?
It is in plain English. MR is the beam capacity, okay,
Yeah, so
and
it
MF
is.
is the moment applied to your beam due to the acting loads. For sure, in order to achieve safe design, the beam capacity has to be more or equal the moment comes from the load. Otherwise, if your beam doesn't have enough capacity, it means mathematically less. Okay, it means your beam will fail. As simple as that. Any other question? Any other question? Okay, so let's move on to the next slide. So guys, although I said here that in our life as a designer, we will face those different problems. Sometimes we do check and sometimes we do design. And I know our course is the name is called design, so probably we will focus much on the design. However, really the good understanding of the beam behavior can be totally understood from the when we do the check. Okay, so for in this class here, I will work with you guys some examples with numbers so you guys understand the beam behavior and how do we know whether a beam is going to fail in a tension mode or balanced mode or compression mode. Okay, now guys, let me ask you. So on the left side here, I'm going to box out this beam. So we are given a beam, and this beam, as you can see, it has a width of 400. It has a depth of 700. It has some rebar. How many? We have 325 M bars. And so we know the number is 3 and the size is 25. Some other information like the FC dash, the concrete strength is 30, and F field is 400. Okay. Can anybody in this class look at this beam and eyeball it and say, you know what, this beam is going to fail in tension or balance it or compression? Can anyone do that just by looking at the section? If you can, let me know.
I think it would fail in tension.
Is that Brody?
Yeah.
Brody, like, can I ask you, like, you it looks like you're very talented. Can you tell me how did you get that? Like, how did you know?
Looking at the rebar there, it's only on the bottom, unlike our other ones, which were overly reinforced. Like this only has the 3 bars.
Okay,
So,
are you referring to the cross section that I gave to you in the last lecture where you have 3 colors, like the 3 colors,
yes.
like cyan and magenta and I think yellow or something?
Yes, this only has the 3 main bars.
Okay, okay, thank you. Anybody else has another input to kind of eyeball this beam and say, okay, you know what? I think this beam will fail in tension or fail in compression or balance at failure.
Wouldn't would
It,
wouldn't
it,
it like what type of load put on it would make a difference too, though, right?
You know what? Like, listen to me, please. Like, you know, you know, it's not when we say beam will fill in tension or compression or balance at failure. This has nothing to do with the applied load. This is a different discussion. When we say safe or unsafe, then we have to see what is the applied bending moment so we can compare the capacity with the applied bending moment. But here, for checking the failure, the assumption here is I'm going to keep adding load, keep adding load, keep adding load until I arrive to the failure point of this beam. And at the failure, it will fail either in balanced or tension or in compression. Does this make sense for you? Or I'm speaking very fast?
Makes sense.
Okay, so please, when I say tension, compression, or balanced, please don't think about the applied load. This has to do with the which one will fill first. My concrete in the top will fill first, or my rebar on the bottom will fail first, or both of them they will fail at the same moment. Again, my question one more time is, does anyone in this class is talented enough to just look at the beam that has 325 M with this dimension FC dash and say whether the beam is going to fail in tension or in compression or balanced?
this is properly reinforced actually, and I think Brody is right.
Okay. Guys, listen, my question kind of was a joke because simply we cannot really look at just the rebar and we can say right away that this is balanced or tension. It looks like we have to do some calculations, okay? And the calculations are the only one will tell us whether our beam is properly reinforced or over reinforced or balanced. And I'm going to take you through this exercise in a minute. But really, what I'm trying to say here is that in order for us to understand whether our beam is going to be properly or over or balanced, then we have to calculate. Okay, are you following? Okay. Looks, guys, today you're so sleepy. I see sleepy faces. Anybody would like to have a discussion? Would like to say something interesting? Looks like my class is boring. I'm open the floor right now for discussion. Forget
I would
about
like to
complete.
finish that coffee that I got. That would help.
Okay, yeah, good for you. You know what? I have some tea here. I'm not doing coffee, but I do tea every morning. I haven't finished my tea yet.
No, it's not boring, sir. It's actually interesting. We just keep quiet because we wanted to listen.
Yeah, but you know what? That's from your perspective. But from my perspective, I need somebody to say, because I don't see your faces, and I'm a person that also always teacher looks at people's faces, and that's part of our job, by the way. We look at people's faces, and we know whether they follow or they don't follow. You can imagine my hard job. I'm trying to speak, and I don't get any back. And I'm not saying it has to be continuous, like 24, like the whole 2 hours, but at least I have to do kind of temperature check every few minutes, at least to see if I'm doing right or wrong. Okay? So can we do some noise, please?
Don't worry, we will interrupt if you think you're doing wrong.
Okay, thank you so much. Okay, so let's move on and show you how do we do the magic that whether the beam is properly reinforced or overly reinforced or balanced failure. Now, guys, very important, very important to the diagram that you can see. So you can see here on the left side, you still see exactly my beam. However, on the right side here, you see something called stress diagram. So I'm gonna type it in here. So this thing here is called stress diagram. And so the stress diagram, it means I'm showing the variation of the stress along the cross section in a side view, if you will. So you can see here at the very bottom, we have some tension force in our rebar. I'm using here T sub R to represent the tension force in my rebar. And remember, tension force, not stress, huh? Tension force. Now on the top part here, if you guys remember the yellow one. So this guy, I'm gonna point an arrow to the what I'm saying here. So this box here or this rectangle here, does anybody in this class remember from last class discussion, what do we call this box? Does it have a name in our class?
It's something to do with the similar rectangular shape for the centroid.
You're saying good stuff and bad stuff together. So you're saying similar.
Yeah,
It's called, okay, you know what? I kind of feel that where you're getting, but it's called equivalent. Equivalent. So we're not using similar,
yeah,
huh?
not similar, equivalent. That's the word I was looking for.
Equivalent rectangular block. And simply this block replaces the parabolic shape, which is the stress in the concrete. So the actual stress in the concrete, it's parabolic shape. It's non-linear, which is very hard to deal with mathematically. However, what we did last class is we replaced this parabolic shape by equivalent rectangular block. And I said why? Because simply it is easy to deal with it mathematically. That's the only reason. And I said, guys, remember, I said also in my class from this point on, you will not see any parabola. You will always see the equivalent rectangular block. Guys, listen. The neutral axis is not shown here. So the actual neutral axis is somewhere here. So the neutral axis is somewhere here. And the neutral axis is simply a distance c, little c from the top fibers. Okay, it's not shown here. However, I'm showing only the A, which is the depth of the equivalent compression block. Okie dokie. And also, guys, do you remember what is this dimension? I'm going to point out from here to there. Does anybody remember this value? How much this value is from last class?
It's alpha 1 pi c. I mean pi c
Yes,
F prime C.
exactly, guys. Thank you so much, Jelly. I will just have to give you a couple of marks for that. Thank you. Okay, so true, guys, this dimension is equal to alpha 1, which is a modification factor to create the rectangular shape, multiplied by phi c, 0.65, multiplied by f prime c. Okay, now all we have to do in this case, we simply have to find what should be the total tension force in my rebar. So I'm referring to this number, guys, this number here. So this number here, can we find this number? Not very difficult. Remember, T sub R here is a force, and the force is equal to stress multiplied by area. Do you guys agree? A force is equal to stress multiplied by area. So what is the stress? The stress is here. So this is the stress in your rebar. Okay? And so I know some of you will say, hey, Tahir, you have something is not right. Why you say here that the stress in the rebar is equal to F field while you said that we have three different failure mode and the stress in the rebar, it depends on what's the failure mode. Okay, if you don't remember that, go here. For example, what was the Fs here in the balanced is equal to F field. How about what is in compression failure? What is the Fs is less than F field. And how about the tension failure? The Fs is equal to F fields. So which means not all the time, the stress in the rebar is equal to F field. And that's why, please read this statement. Please read this statement. I said here, let's assume that rebar has yielded at failure. Let's assume that rebar has yielded at the failure. And because of this assumption, and I know some of you will say, why do you assume? So I'm going to give you my first golden rule in this class. First golden rule. Please listen to me. Assumptions are great. They make our life easy. However, we have to check them to validate our assumption before we take a decision. Okay? So we can certainly, in my class, you will see, I will do lots of assumption. You will start them coming probably next class when we start the design. But you will see, once we assume those assumptions, they will make our life easy, super easy mathematically. But you will see at some point I will have to come back and verify my check. So it's okay right now to assume that my rebar has yielded, given that later on, before I finalize my conclusion, I need to make sure that this was true. I'm going to show you how. But for now, when I say my rebar has yielded, mathematically, the F sub S, which is the stress in the rebar at the failure, is equal to F field equal to 400. And look at how easy the math will become. So you can see here I'm multiplying a stress. And please, also, if you remember, I said this several times, that you will never ever see F field by itself. It is always F field multiplied by its reduction factor or resistance factor, phi sub S. So we take 85%, 85% of 400. We never deal with the 400. And then we multiply the area of the steel, and because we have a 325M, 325M, and if you go back to the chart or the table that tells you what's the area of the 25M, you will find out that every 25M, the cross-section area is 500 square millimeter, which is here. So this is where I estimated the total area of steel. Guys, remember that this area of steel does not include any other rebar. It includes only the main reinforcement. This means if I have here some rebar on the side, and we call them skin reinforcement, those are not included. Those are not included. If I have some rebar here, which we call them stirrup hangers, so those also are not included. So what's included area of steel only is this portion here, which at the very bottom of your beam. Those are called the main reinforcement, and those are the primary resistance for your moment. Okay. Now you can see all you have to do is you multiply your stress by the area, and also remember the units. Units are very, very important. When we say 400, it's MPa, and MPa is Newton per millimeter square. If you multiply Newton per millimeter square times millimeter square, obviously you get the force T in Newton. And very simple, if you divide by 1,000, then congratulations, now you have the total tension force in your rebar in kilonewton, 510. This number, huh? So this number is what? This number is the total tension force in your rebar. Now, guys, you will see that we said probably the first day we talked about statics, and for anything to stay in place, looks like there should be equilibrium between forces and moments. Okay, so what happens here? We have a tension in my rebar as TR, and we have a compression in my concrete as CR. What should be the relationship between the TR and CR? What do you think? It is always they have to balance each other, because simply my section is now going to the left or to the right, stays in place. So my forces, sigma x or sigma forces in the x direction equal to 0. It means my CR equal to TR. Now, so if you're saying that CR is equal to TR, and we know my TR is equal to 510 kilonewton, it means I know how much is my CR. And now let's see, we already replaced the TR by area multiplied by stress. Would you agree? So in this equation here, I replaced my TR by stress multiplied by area. Can I do the same thing here? Can I replace my CR by area times stress? Yes, you can, and I'll show you how. So guys, you will be surprised if I just mark this, if I mark this number, and I will say this is your stress. This is the stress. As Jelly said, I guess she said, I asked her about this dimension in my block diagram. She said alpha 1 phi c f prime c. And again, you have a 25 MPa concrete, you multiply times 0.65 unitless, and then you multiply times 0.8, which is alpha 1. So this whole term is, it's a stress. Okay? So guys, the stress here, you have to multiply it by area. So what's the area? One dimension of the area is simply the A. The A, which is the depth of the equivalent compression block, is A here. So that's one dimension of the area. However, the other dimension is called B. And guys, do you remember what was B?
The width of the beam.
The width of the beam. And unfortunately, you cannot see in the stress diagram, you cannot see the width of the beam because simply it's perpendicular. However, I can tell you, please watch this. I'm going to show you something here. So guys, this here, this rectangle here, this rectangle here is simply your the area exposed to the stress. So so you can see here, this rectangle, I'm not sure if I can hatch. Let's say this. So this rectangle here is the rectangle exposed to the stress. So the value of the stress is alpha 1 phi c fc dash. And the dimension of this is what? It's simply the depth is A, and the width from here to there, this width is equal to the width of your beam. So hopefully you guys can follow that. So you can see the C sub R is equal to stress, which is alpha 1 phi c f prime c multiplied by the area, and the area is here in yellow. The area is B multiplied by A. Okay. When we do so, you can see. Look at what we have and what we don't have. So alpha 1, what do you think? Let me ask you guys, and please speak out. Speak out, please. What's the value of alpha 1?
0.8.
So the alpha 1 is 0.8. Thank you so much. Somebody else, please. How about the phi c?
.65.
Okay. Fc dash is your concrete compressive strength, which is known for our beam. Okay. How about B? It's the width of the beam. Again, remember we're solving this beam here, and the beam width is 400, and the Fc dash is somewhere here. It's a 30 MPa. So guys, this means everything is known except this number here. So this number, which is the depth of the equivalent compression block is called A. So what we can do simply is by working the math out, and we can find the value of A. So you can see the value of A is 81.7 millimeter. 81.7 millimeter. Okay. Now, once you know the value of the A, because of the equilibrium of C and T, then we simply go to our strain diagram. Okay, so one more time here, you can see I kind of exactly copied the picture from the previous slide. So that's exactly the same beam, and we have the compression in the concrete, we have tension in rebar, but also what I did is I draw this strain diagram. Remember, this guy here is called stress diagram, and this guy here is called strain diagram. Please don't be confused. This is a stress and this is a strain diagram. So this is the strain diagram, and from the strain diagram, you will see, we will figure out what is the type of the failure. Okay, so let me show you. So guys, you can see, I think I have a little typo. So guys, please forgive me. I have to correct this part. You can see here the beam is different. So this 650 and 700. However, this beam is 450 and 500. So this is something I have to correct and re-upload. So those number, please use the other number from other page. Okay. However, everything else here seems to be correct. So now, something very, very important. Please pay attention. If you have been sleeping from the start of the class, please wake up now. Wake up, guys. Now, you can see here, I got here A is equal to 81.7. However, on my diagram here is the dimension is 90.8. Is anybody seeing why this 90.8 and this one is 81.7? Does anyone see why they are different?
Because your A is only the height of that where the arrow thing is, and your 90.8 is the distance from neutral axis to the top one, meaning you have to find the centroid of that the centroid of the thing of this member.
Thank you so much. You got 5 marks for that. Although I know the numbers are written on the slide, but the way you said it, it looks like you're following 100% what I'm saying here. Guys, I'm trying to warn you here. So you can see the stress equivalent block in yellow. It's the dimension is A. That's called the depth of equivalent rectangular block. However, the neutral axis is a little bit below, and I mark it here with NA. And remember, neutral axis, it means it has zero stress and it has zero strain. And that's where my strain comes to zero at the neutral axis. Remember the relationship between the A and C. And remember, A is the depth of the equivalent rectangular block, and C is the location of the neutral axis. The relationship is very simple, is through the beta 1, and beta 1, we agree in my course, is going to be 0.9. So all we have to do is, after we find the A is equal to 81.7, we divide by 0.9, we get C is equal to 90.8, which marks the zero of the strain. Now, again, you can see in my diagram here, I'm going to zoom in. So here is my strain diagram. C is 90.8, and because the D is equal to 650, then whatever left from 650, this will be the base of the other triangle, okay? The base of this triangle, okay, guys, I'm referring, so from here, from this point to this point here, that's 90.8. And the effective depth of your beam to the center of the rebar is 650. And so which means from this point to this point here is simply 650 minus your 90.8, which is D minus C. So this is 595.2. Now, you can see what I did is I just assumed here, and because I don't know so far, I don't know whether my beam will fail in tension or compression or balance it. So generally speaking, I assume that this is epsilon S. So I never said is equal to or more or less than epsilon yield, okay? So what has to happen here is I'm going to use this triangle here or this geometry here to simply determine how much is my epsilon S. Is that very difficult? That's pure math. Similarity of triangles. So you can see I colored them with different color in maybe red and somehow pink. So you can see all you have to do is you do similarity of triangles and you will be able to find out the value of epsilon s. Let's see how. Okay, it's over there. So epsilon s in the yellow triangle divided by 595.2. This equals in the other triangle 0.0035 divided by 90.8, which is here. So on this side here, this is exactly what I said a minute ago. So from this similarity of triangles, we can simply find the strain in the steel. Now the question is, so we found out the stress in the steel, sorry, the strain in the steel equal to 0.021, 0.021. Now, very simple. All you have to do is compare this number against your epsilon yield. Okay? And guys, remember, I mentioned it here probably once and for good. I said here epsilon yield is equal to 0.002 for rebar grade 400 grade. Okay? Does anybody doesn't know how to find this number? How do you find the strain in the rebar for 400 grade?
From the
Simply,
table.
it's not from the table, it is from the modulus of elasticity of 200,000 MPa. So this number is equal to 400 divided by the modulus of elasticity, which is 200,000, you will get 0.002. And remember, since in my class all the time, we're going to use this rebar grade, so all the time in my class, the yield strain is equal to 0.02. So it's as simple as once you find the actual strain in your rebar before your beam failed, then we know whether our beam has failed in tension or compression or balance. Can anybody tell me based on what you see right now? Okay, so the strain in the steel is way larger than the epsilon yield, which is 0.02. Okay, can anybody tell me, is that balanced failure or tension failure or compression failure?
Tension failure.
Can anybody else tell me if it's tension failure or compression failure or balance failure?
Tension failure.
Okay. Anybody else? Guys, again, the only thing I can understand that you're following is you answer my question. Okay, so please don't be quiet because it tells me that nobody's following. One more time, if I'm able to, from the similarity of the triangle, using this math here and this diagram over there, I found out that strain in the rebar when concrete fails, it's already 0.021. And for a 400 grade, this number, so I can write it here, this number is equal to 0.002. Okay, that is the strain in the rebar at yields for 400 grade. Okay, you can see the 0.021 is way higher than 0.002. Let me ask you, is that tension failure? Is that compression failure? Is that balanced failure? Maybe I can rephrase my question. Are we after the yield point or at the yield point or before the yield point?
It's after the yield point and it's tension failure.
Okay, thank you, sir. Correct. Thank you, Gord. So this is exactly what's happening, guys. If you don't know why, let me draw for you the strain diagram very quickly. So here is my strain diagram or stress strain diagram for rebar. It goes from 0 and it goes in a line relationship to the yield, and then it goes horizontal until the necking and the failure. So guys, listen, let me show you some dimensions. So dimension from this point here to the yield, this number is 0.002. That is for 400 grade. However, really the strain at the failure, it was 0.021. So it looks like it's 10 times, about 10 times. So this 0.021, okay? And which means my failure, let's extend this guy here. So it looks like my failure was here, which means my beam failed when I already passed the yield point. Remember, the yield point is here. This is the yield point, which means it's a tension failure. And what does it mean, tension failure? It means my rebar has yielded, and my assumption, which I assumed here. So guys, you can see here is how I verified my assumption. So you can see in plain English below, this means the assumption was true, and Fs, yes, it was equal to F yield. How is that? Let me show you at the failure. So this is the failure point, okay? This is the failure point. So what is the Fs at the failure? It's this much, huh? So this much is my stress in the steel. So this was 400, huh? Was 400. So at the failure, the stress was equal to F yield. And guys, it means mathematically all my numbers were right. Would you agree or disagree?
I would agree with that.
Okay, you can see assumptions are great. Assumptions are great. So I did an assumption here. However, we cannot just come up with conclusion without verifying the assumption. And that's how I verified my assumption. Okay? Are you following, guys?
Yes.
Okay, listen. Next is, and we will break after this. So next is, after I found out my beam is tension failure is a properly reinforced there. So I know based on what I have done is my beam is properly reinforced. Can I find what is the capacity of my beam? When I say capacity, it means how much is my M sub R. M sub R is something called the moment of resistance, or in plain English called capacity of the beam. Can we find for this beam here, can we find what is the moment of resistance? Okay. We can do that. Please watch me.
Yes.
So please watch me. I'm going to show you right now on how to find the moment of resistance or the capacity of your beam. Very simple, very, very simple, not super science. You guys see that also we have here, that's the strain diagram, and on the right here, that's the stress diagram. Look at the stress diagram. You can see everything is known. So far, we know the A is equal to 81.7, which is correct. We also know that the tension force in my rebar is equal to phi S multiplied by F yield multiplied by S, okay? And also you see that my CR, which is the total compression force in my concrete is equal to alpha 1 phi C FC dash multiplied by A multiplied by B. Okay, I just replace all the symbols by numbers, huh? So we know how much is my total compression in my concrete. Something also probably so far we never pay attention to, there's something called lever arm, huh? Lever arm. So the lever arm is simply between the red arrows. The red arrow. So you can see this red arrow at the bottom is my total tension in my rebar. The red arrow in the top is my total compression in my concrete. In between, there is a lever arm. Lever arm, how much? Very, very simple. If you're telling me is from top to the center of the rebar is D, and you're telling me that this whole dimension is A, looks like C is going to be in the middle of the A. Would you agree? Because it's a rectangle, huh? And that's, you see the beauty of turning our parabola into equivalent rectangular block. It means my force is in the middle. Just like you guys remember first class or second class when I talk about statics, and we replace the entire uniform load by a point load in the middle. Same thing here. So we can replace this block by a point load in the middle. So you can see the location of this red arrow is in the middle of A, and which means the lever arm is very simple, is equal to D minus E over 2, D minus E over 2, okay? So very simple. If you want to find how much this beam can resist in terms of bending moment, you have to multiply your T times lever arm, and you can get the same results if you multiply C sub R multiplied by lever arm, okay? Very simple. In our class, let's agree. You need to do both. You need to find the moment from the compression. You need to find the moment from the tension, and you have a check. Those numbers must agree. Okay, please take a note that we need to find the MR from tension and from compression, because this is a mathematical check, because you don't know, maybe along the way you have done any mathematical error, and simply if those numbers do not agree, it means your calculation somewhere here you have done a mistake. So that's why if we do it from tension and compression, we kind of check our results. The numbers must agree. I've done it myself, and it's 310.67 and 10 to the power 6. Okay, remember guys, units very important in any course, especially in my course. So anytime you want to write something, please make sure you include the units. I'm not saying about those individual numbers. However, your final results, you must show the units. Let me ask you, and I need somebody to help me very quickly. What are the units of this number, or what's the units of this number? 1500?
mm squared.
Thank you. How about the units of this guy? 400?
MPa.
Thank you so much. Newton per millimeter square. And this guy is? That's the G, huh? The effective depth. Millimeter. And how about the A? It's a distance. Okay. So you guys, you can see here, everything is measured in Newton and millimeter. And that's why your moment will be Newton millimeter. And you can see it's so big, huh? And that's not the norm, huh? We typically do not use Newton millimeter for moment. We always use kilo Newton meter, and it's as simple as you just divide by 10 to the power 6, and then you get your moment. Any questions so far? Any questions so far?
Not yet.
Okay, so guys, go ahead.
Sir, for example, if you want to check if that beam is stable or unstable, how do you calculate MF?
That's a different, and it's coming in the next slide. So if you wait for a few minutes, you will see next slide. After the break, you will see that.
Okay.
Okay, so after the break, we will talk about this one. Okay, so guys, for now, any other question? Any other question? Okay, so guys, I will see you guys in 10 minutes. So we'll come back here at 9:04. Thank you.